This course is a comprehensive blockchain technology course that covers a wide range of topics that teaches blockchain technology, its applications, and its underlying concepts. We will cover everything that you need to know to become a blockchain technology expert in a very simple and basic way. Here's a list of essential modules that this blockchain technology course will cover. Module 1, Introduction to Blockchain Technology. The following will be covered: blockchain definition and core concepts, an overview of blockchain technology's history and evolution, and analysis of traditional database systems. Module 2, Cryptocurrency Basics. The following will be covered: cryptocurrencies and tokens explained, introduction to Bitcoin and Ethereum, the two most well-known cryptocurrencies, mining, algorithms, and proof-of-work and proof-of-stake mechanism. Module 3, Blockchain Architecture. The following will be covered: understanding blockchain's decentralized architecture, components of a blockchain network, nodes, blocks, transactions, and the blockchain itself, public versus private blockchains. Module 4, Smart Contracts. The following will be covered: definition and use cases of smart contracts, programming smart contracts using languages like used for Ethereum, creating and deploying simple smart contracts. Module 5, Blockchain Security. The following will be covered: cryptography, fundamentals, and its role in blockchain security, cryptocurrency, consensus algorithms, which include proof of work, proof of stake, delegated proof of stake, blockchain, vulnerabilities and attacks, best practices for blockchain security. Module 6, Use Cases and Applications. And the following will be covered: real-world applications of blockchain beyond cryptocurrencies, examples in supply chain, healthcare, finance, case studies of successful blockchain implementations. Module 7, Blockchain Development. The following will be covered: setting up a development environment for blockchain projects, developing decentralized applications, interacting with blockchain networks using APIs and SDKs. Module 8, Blockchain Governance and Regulation. The following will be covered: exploring the regulatory landscape for blockchain and cryptocurrencies, governance models in blockchain network, legal and ethical consideration. Module 9, Future Trends and Innovations. The following will be covered: emerging blockchain technologies, blockchain's potential impact on industries and society. Module 10, Ethical and Social Implications. The following will be covered: discussing the social, economic, and ethical implications of blockchain technology. So let's get started to cover each module in detail. Introduction to Blockchain Technology. We will learn the following: blockchain definition and core concepts, an overview of blockchain technology's history and evolution, and analysis of traditional database systems. Blockchain technology definition and core concepts. Blockchain technology is a decentralized and distributed digital ledger system that enables secure and transparent record-keeping of transactions across multiple participants. It provides a way to achieve consensus in a trustless environment, eliminating the need for intermediaries while maintaining data integrity. The core concepts of blockchain technology include decentralization. Unlike traditional centralized systems, where a single authority controls a database, a blockchain operates on a decentralized network of nodes. Each node has a copy of the entire blockchain, ensuring redundancy and reducing the risk of a single point of failure. Distributed ledger. The blockchain is a chain of blocks where each block contains a set of transactions. Every participant in the network has access to the complete history of transactions, making it a distributed ledger that is transparent and mutable. Consensus mechanism. To validate and add new blocks to the blockchain, participants must agree on the state of the ledger. Various consensus mechanisms like proof of work, proof of stake, and more ensure that the participants agree on the transactions before they're added to the chain. Cryptographic security. Transactions in a blockchain are secured using cryptographic techniques. Each block contains a hash of privacy block, creating a link that makes alternating past blocks extremely difficult. This ensures data integrity and preventing tampering. Smart contracts. Smart contracts are self-executing contracts with the term of the agreement directly written into a code. They automated and facilitate transactions between parties when specific conditions are met, thus removing the need for intermediaries. Immutability. Once a transaction is added to the blockchain, it becomes nearly impossible to alter it. This immutability, achieved through cryptographic hashing and consensus mechanism, ensures the integrity and authenticity of data. Permission versus permissionless. Blockchain networks can either be permissioned, meaning private, or permissionless, meaning public. Permissioned blockchains restrict access and participation, while permissionless blockchains allow anyone to join the network and participate. Now let's move on to history and evolution of blockchain technology. Early concepts. The foundational ideas of blockchain technology can be traced back to the 1980s. However, the concept gained traction with the publication of the Bitcoin white paper in 2008 by an individual or group using the pseudonym Satoshi Nakamoto. Then comes Bitcoin and cryptocurrencies. The first implementation of blockchain was for the creation of the cryptocurrency Bitcoin. Bitcoin's blockchain served as the digital ledger for recording transactions without the need for intermediaries. Then comes Ethereum and smart contracts. Ethereum, introduced in 2015, expanded the capabilities of blockchain by introducing a programmable platform for creating decentralized applications, dApps, and smart contracts. Diversification of use cases. Beyond cryptocurrencies, blockchain found applications in various sectors, including supply chain, management, healthcare, finance, voting systems, and more. Different blockchain platforms merged to address specific use cases and industry needs. Scalability and interoperability. Blockchain technology faced challenges related to scalability, energy consumption, and interoperability between different blockchains. Efforts were made to improve these aspects through innovations in new consensus mechanisms. Enterprise adoption. Businesses started exploring blockchain for its potential to enhance transparency, traceability, and security in their operations. Alliances were formed to develop industry-specific blockchain solutions. Now let's move on to the analysis of traditional database systems. Traditional database systems and blockchain technology have distinct characteristics. Centralized versus decentralization. Traditional databases are centralized, managed by a single entity. In contrast, blockchains are decentralized, distributing control among various participants. Data control and ownership. In traditional databases, data control and ownership reside with the database administrator. Blockchains allow participants to have ownership and control over their data. Trust and intermediaries. Traditional databases rely on trusted intermediaries to validate transactions. Blockchains achieve trust through consensus mechanism, reducing the need for intermediaries. Data integrity. Traditional databases can be susceptible to data manipulation, while blockchains provide strong data integrity due to cryptographic hashing and various mechanisms. Transaction speed and scalability. Traditional databases often offer higher transaction speeds and scalability compared to blockchains, which can face limitations due to consensus mechanisms. Immutable versus editable data. Blockchains provide immutability, making it difficult to alter past transactions. Traditional databases allow for easier data modification. In conclusion, blockchain technology revolutionized how data is stored, shared, and transacted by introducing decentralization, cryptographic security, and trustless consensus mechanisms. It has evolved beyond its origin in cryptocurrencies and found diverse applications across industries, while also promoting discussions about its limitations compared to traditional databases in terms of scalability and speed. Cryptocurrency basics. We will be learning the following: cryptocurrencies and tokens, introduction to Bitcoin and Ethereum, the two most well-known cryptocurrencies, mining, consensus algorithms, and proof-of-work / proof-of-stake mechanisms. So let us get started with cryptocurrencies and tokens overview. Cryptocurrencies and tokens are digital assets that operate on blockchain technology. Let's break down the concepts of cryptocurrencies and tokens along with some examples and key points. Cryptocurrencies. Cryptocurrencies are digital virtual currencies that use cryptography for security and operate on decentralized networks called blockchains. These blockchains maintain a secure and transparent ledger of all transactions involving the cryptocurrency. The first and most well-known cryptocurrency is Bitcoin. Key points about cryptocurrencies. Decentralization. Cryptocurrencies are typically decentralized, meaning they are not controlled by any single entity, government, or central bank. Blockchain. Transactions are recorded on a blockchain, which is a distributed and immutable ledger. Cryptography. Cryptocurrencies use cryptographic techniques to secure transactions and control the creation of new units. Limited supply. Many cryptocurrencies have a predetermined supply limit, like Bitcoin's cap of 21 million coins. Digital ownership. Owning a cryptocurrency means having a cryptographic private key that grants access to the associated digital wallet. Examples of cryptocurrencies are Bitcoin, the first cryptocurrency created by an individual or group under the pseudonym Satoshi Nakamoto. It introduced the concept of blockchain and remains the most well-known and valuable cryptocurrency. Ethereum. Beyond being a cryptocurrency, Ethereum introduced the concept of smart contracts, which are self-executing contracts with the terms of agreement directly written into the code. Ripple. Designed for fast and low-cost cross-border payments, Ripple focuses on facilitating real-time, secure, and cost-efficient global transaction. Tokens. Tokens are units of value issued on existing blockchains, often to represent assets or access to specific functions within a decentralized application, also known as DApp. Tokens can have various use cases, from representing digital assets to enabling voting in decentralized governance systems. Key points about tokens. Built on blockchains. Tokens are built on existing blockchain platforms like Ethereum, BS Smart Chain, and others. Smart contracts. Tokens are often created and managed through smart contracts, enabling customized functionalities. Utility tokens versus security tokens. Tokens can be characterized as utility tokens, providing access to specific services or features, or specific tokens representing ownership in a real-world asset. Initial coin offerings, ICO, and token sales. Projects can raise funds by selling tokens in ICOs or token sales, providing early investors with a stake in the project's ecosystem. Examples of the tokens are Chainlink, a utility token on the Chainlink network, providing decentralized Oracle services to connect smart contracts with real-world data. Uniswap, a governance taken up the Uniswap decentralized exchange, allowing holders to participate in decision-making about the platform's future. Tether, a stable coin pegged to the value of a real-world asset like the US dollar, providing stability in a volatile cryptocurrency market. Let's move on to introduction of the Bitcoin and Ethereum, the two most well-known cryptocurrencies. Bitcoin. Introduction. Bitcoin, often referred to as the digital gold, and it was the first currency that was ever created. As mentioned before, it was introduced in a white paper published by an individual or group using the pseudonym Satoshi Nakamoto in 2008. Bitcoin's main purpose was to serve as a peer-to-peer electronic cash system, allowing users to conduct transactions without the need for intermediaries like banks. Ethereum. Introduction. Ethereum, introduced by Buterin in 2015, goes beyond being just a cryptocurrency. It's a decentralized platform that enables developers to build and deploy smart contracts and decentralized applications, also known as DApps. Smart contracts are self-executing contracts with terms directly written into the code. Some of the key points to keep in mind and an example. Let's start with Bitcoin. Decentralization. Bitcoin operates on a decentralized network of computers, collaboratively known as the Bitcoin network, is not controlled by any central authority. Blockchain transactions are recorded on the Bitcoin blockchain, a public and transparent ledger that stores all transaction history since its inception. Mining. New Bitcoins are created through a process called mining. Miners used powerful computers to solve complex mathematical problems, and in return they're rewarded with neurally created Bitcoins and transaction fees. Limited supply. Bitcoin has a fixed supply limit of 21 million coins. This is built into the protocol and contributes to its value proposition. Security. Bitcoin transactions are secure through cryptographic techniques, ensuring the integrity and privacy of the transaction. Let's look at the Bitcoin example. Let's use Alice, who wants to use 0.1 Bitcoin to bomb. Alice initiates a transaction by signing it with her private key. The transaction is then broadcasted to the Bitcoin network, where miners validate and add it to the block on the blockchain. Once confirmed, the transaction is irreversible and Bob now owes 0.1 Bitcoin. Now let's move on to Ethereum. The key points to note are smart contracts. Ethereum's unique feature is the ability to create and execute smart contracts, automating complex processes without intermediaries. Decentralized applications, DApps. Ethereum hosts a wide range of DApps spanning from decentralized finance platforms to digital art marketplaces. This is interesting. Ethereum gas. Transactions and smart contract executions on Ethereum requires gas, a fee paid in Ethereum to incentivize miners to process operation. Upcoming transition. Ethereum is transitioning from a proof-of-work consensus mechanism to a proof-of-stake mechanism with Ethereum 2.0. This aims to improve scalability and energy efficiently. Now let's just quickly talk through a Ethereum example. Imagine Alice wants to create a decentralized prediction market, the app on Ethereum. She writes terms of the prediction market into a smart contract. Users can then participate by placing bets using Ethereum. The smart contract automatically calculates winners based on the outcome, distributing rewards accordingly, all without any centralized intermediary. Bitcoin and Ethereum have significantly influenced the world of cryptocurrencies and blockchain technology. While Bitcoin mainly focuses on being a digital currency and store of value, Ethereum has expanded the possibility by introducing programmable smart contracts and enabling a wide range of decentralized applications. Let's talk about mining, consensus algorithms, and proof-of-work, proof-of-stake mechanisms. Mining. Mining is the process of validating and adding new transactions to a blockchain, ensuring the security and integrity. It involves solving complex mathematical problems using computational power. Miners compete to solve these problems, and the first one to find a solution gets the right to add a new block of transactions to the blockchain. In return for their efforts, miners are rewarded with newly created cryptocurrency tokens and transaction fees. Key points to keep in mind. Block creation. Miners create new blocks of transactions by solving cryptographic puzzles. Incentives. Miners are incentivized with rewards, newly minted tokens, and transaction fees for contributing power. Security. Mining secures a blockchain by making it computationally expensive to alter transaction history. Energy consumption. Proof-of-work mining can be energy intensive due to the power required to solve these puzzles. Now let's move on to consensus algorithm. Consensus algorithms are protocols that ensure all participants in a decentralized network agree on the state of the blockchain. They prevent issues like double spending and maintain the integrity of the blockchain's transaction history. Different consensus algorithms have different ways of achieving this agreement. Key points to keep in mind. Decentralization. consensus algorithms enable agreement in a decentralized network without relying on a central authority. Byzantine fault tolerance. They're designed to function even when some network participants are mal or faulty. Variety. Various consensus algorithms exist, including POWPOS, delegated proof of stake, practical Byzantine fault tolerance, and much more. Now let's talk about proof of work. Proof of work is a consensus algorithm used in many early blockchain networks, most notable in Bitcoin. In proof of work, miners compete to solve cryptographic puzzles, and the first to solve it gets a new block of the blockchain. Key points to keep in mind. Security. Proof of work has proven to be secure due to the computational effort required to solve puzzles. Miner competition. Miners compete to solve puzzles, and the fastest one gets to add the block. Energy intensive. Proof of work can be energy intensive, so miners need substantial power to solve these problems. Proof of stake. Proof of stake is an alternative consensus algorithm that doesn't rely on solving complex puzzles. Instead, validators are chosen to create new blocks and validate transactions based on the number of tokens they stake as collateral. Key points to keep in mind. Validator selection. Validators are selected to propose and validate new blocks based on the tokens they hold and mark as stakes. Energy efficiently. POS is considered more energy efficient compared to POW, as it doesn't require as much as computational power. Security. POS network can be secure if designed properly, as mal validators risk losing their staked tokens. Blockchain architecture. We will learn the following. Understanding blockchain's decentralized architecture. Components of a blockchain network, which includes nodes, blocks, transactions, and the blockchain itself. Public versus private blockchains. Now let us understand blockchain's decentralized architecture. This might seem like repetition as we have covered some points in other sections, but this is really important to understand and emphasize again. Now let's deep dive into the fundamental components of blockchain's decentralized architecture. Number 1. Blocks and chains. A blockchain is composed of a series of blocks, each containing a set of transactions or data. These blocks are linked together in a chronological order, forming a chain. Each block contains a unique identifier called a hash, which is created using the data in the block and the hash of the previous block. The linking of blocks through hashing is what creates the immutability and the security of the blockchain. Number 2. Decentralized network. In a decentralized blockchain network, there is no single central authority or server controlling the entire system. Instead, the network is made up of multiple nodes, which are computers distributed across the world. These nodes work together to validate transactions, each consensus on the state of the blockchain, and maintain the integrity of the network. Number 3. Consensus mechanism. These mechanisms are protocols that ensure all nodes in the network agree on the validity of transactions and the order in which they are added to the blockchain. Different blockchains use various mechanisms. Here are a few examples. Proof of work. Miners compete to solve complex mathematical puzzles. The first one to solve the puzzle gets to add a new block to the blockchain and is rewarded with cryptocurrency. This process requires significant computational power and energy consumption. Power of stake. Validators are chosen to create new blocks based on the amount of cryptocurrency they hold and are willing to stake as collateral. This is considered more energy efficient than POW. Proof of work. Delegated proof of stake. Token holders vote to select a set of delegates who are responsible for validating transactions and creating new blocks. This speeds up the consensus process. Proof of authority. Validators are known and trusted entities often used in private or blockchains. Number 4. Cryptography. Cryptography plays a crucial role in ensuring the security and authenticity of the blockchain transaction. Public and private key pairs are used for digital signatures. When a user initiates a transaction, they use their private key to sign it. Others can then verify the transaction's authenticity using the sender's public key. Number 5. Immutability and security. Once a block is added to the blockchain, it becomes extremely difficult to alter, because changing the data in one block would require changing all subsequent blocks, which would require the consensus of the majority of the network. This immutability makes blockchain highly secure for storing sensitive data. Number 6. Peer-to-peer communication. Nodes in the network communicate with each other in a peer-to-peer fashion. This means that each node has a copy of the entire blockchain, and they share updates and validate transactions without relying on a central authority. Number 7. Incentive structures. Many decentralized blockchains include incentive structures to encourage participants to contribute to the network. And POW miners are rewarded with cryptocurrency for validating transactions, and POAds validators earn transaction fees and network rewards for participating in consensus. Number 8. Smart contracts, which is optional. Some blockchains support some smart contracts, which are self-executing programs that automatically execute contract terms when predefined conditions are met. This enables automation of complex processes and eliminates the need for intermediaries. Understanding these key elements will give you a solid foundation in grasping the decentralized architecture blockchain technology. Remember that while the core concepts are similar, different blockchain platforms may have unique features and implementations. Let's now move on to the components of a blockchain network, which includes nodes, blocks, transactions, and the blockchain itself. Number 1. Nodes. Nodes are individual computers or devices that participate in a blockchain network. Each node has a copy of the entire blockchain ledger, which contains the record of all the transactions. Nodes communicate with each other to validate transactions, reach consensus, and maintain the network's integrity. There are different types of nodes in the blockchain network, such as full nodes. These nodes store a complete copy of the blockchain and validate all transactions and blocks. They play a crucial role in maintaining the network's security and decentralization. Miners or validators. These nodes participate in the consensus mechanism to validate transactions and add new blocks to the blockchain. Miners in proof-of-work networks solve complex puzzles, while validators in proof-of-stake networks are chosen based on the amount of cryptocurrency they hold. Light nodes. These nodes don't store the entire blockchain but rely on full nodes to access and verify transaction data. They are more lightweight and often used in applications with limited resources. Number 2. Blocks. A block is a container that holds a collection of transactions. Each block contains a unique identifier called a hash, which is generated based on the block's content and the hash of the previous block. This linking of blocks through hashing creates a chain in blockchain. Blocks typically include a header, which contains the metadata such as the block's hash, the previous block's hash, a timestamp, and the other information. Transactions, the actual data being recorded on the blockchain, such as cryptocurrency transfers or other digital interactions. Nodes, a random number used in POW to solve cryptographic puzzles and create a valid block hash. Number 3. Transactions. Transactions are the fundamental units of data that represent actions or operations on the blockchain. They can involve transferring cryptocurrency, executing smart contracts, recording ownership changes, or any other relevant activity. Each transaction contains the following: inputs, reference to previous transactions that provide the necessary cryptocurrency to carry out the current transaction. Outputs, specifies the recipients of the cryptocurrency and the amounts they will receive. Digital signatures, generated using cryptographic techniques to prove the authenticity of the transaction and ensure that only the rightful owner can authorize it. Number 4. Blockchain. The blockchain itself is the core structure that holds the entire history of the transaction in a secure and tamper-proof manner. It is a decentralized distributed ledger that ensures transparency, security, and immutability. Key characteristics of the blockchain include decentralization. No single entity controls the entire blockchain network. Instead, it is maintained by the network of nodes working together. Immutability. Once a block is added to the blockchain, it is extremely difficult to alter because it would require changing all subsequent blocks, which require consensus from the majority of nodes. Transparency. Every transaction added to the blockchain is visible to all participants. This transparency contributes to trust and accountability. Security. Cryptographic techniques are used to secure transactions and blocks, preventing unauthorized access and tampering. Consensus. Nodes in the network agree on the validity of transactions and the order in which they are added to the blockchain through consensus mechanism. In some main nodes, blocks, transactions, and the blockchain itself are the foundational components of a blockchain network. They work together to create a decentralized, secure, and transparent system for recording and verifying digital interactions. Now let's talk about public versus private blockchains. Public and private blockchains are two distinct variations of blockchain networks, each designed to cater to different use cases and requirements. Here's a breakdown of the differences between public and private blockchains. Public blockchains. Number 1, accessibility. Public blockchains are open to anyone and everyone. Anyone can participate as a node to validate transactions and read the blockchain's content. This open accessibility is one of the defining features of public blockchains. Number 2, decentralization. Public blockchains are highly decentralized. They operate on a distributed network of nodes, and no single entity or group has control over the network. The decentralization contributes to transparency and trust, as no central authority can manipulate or censor transactions. Number 3, consensus mechanism. Public blockchains often use consensus mechanisms like proof of work or proof of stake to validate transactions and maintain the blockchain's security. These mechanisms require participants to contribute resources or stake cryptocurrency as collateral. Number 4, security. The security of blockchain is achieved through the collective efforts of a large number of participants. The distributed nature of the network and cryptographic techniques ensure the integrity of the data. Some of the examples of public blockchain are Bitcoin, which is the first and most well-known public blockchain used for peer-to-peer digital transaction. Ethereum is another public blockchain platform that supports smart contracts and decentralized applications. Now let's talk about private blockchains. Number 1, private blockchains offer restricted access. Private blockchains, also known as permissioned blockchains, have restricted access. Participants must be granted permission to join the network, which is controlled by a central entity. Number 2, limited decentralization. Private blockchains are less decentralized than public ones. They're typically controlled by a single organization or a group of known entities. This level of control can enhance efficiency and privacy, but might sacrifice some aspect of decentralization. Number 3, consensus mechanism. Private blockchains may use consensus mechanisms like proof of authority or delegated proof of stake. Since participants are known and trusted, these mechanisms prioritize efficiencies over resource-intensive methods. Number 4, security. Security in private blockchain is maintained through the trust established among participants. Since the network is more centralized, security measures can be more tailored and controlled. Examples: Hyperledger Fabric, a permissioned blockchain framework for enterprise solutions providing control over who can participate and access the data. Horda, a distributed ledger platform designed for business transactions and contracts. Before we wrap up, let's talk about choosing between public and private blockchains. The decision to use a public or private blockchain really depends on the specific requirements of the applications. Public blockchains are best suited for applications requiring transparency, censorship resistance, and open access, such as cryptocurrencies and apps that rely on a larger user base. Private blockchains is ideal for scenarios where participants are known and trusted, and privacy and control are important, like businesses, supply chain management, and financial institutions. In some cases, there are also hybrid blockchains that combine elements of both public and private blockchains to strike a balance between decentralization and control.